Okay, I guess I should stand up with this big a crowd. When I just have my regular class in here, I usually sat down because there are only 5 of them. They're all right here. And if I keel over, I left my office in time to, in normal traffic, have dinner. I got here with 5 minutes to spare. So just, feed me something. All right. Now, this talk is really intended as a professional colloquium. So if I say something that's, I don't understand the background of that, I have teenagers. Just yell, stop me, and I'll go into the background because I have plenty of time. I'm used to being interrupted. I haven't completed a thought since 1989. I'm going to talk about. First, I'm going to introduce the subject, and then we have 2 events that are basically really strange precipitation events that do things that affect the atmosphere all the way to the ground, as far as we can tell, electrically. And that's quite unusual. One of them, the January 27th, 2003 event, is 60 MeV protons, I think, and it appears to be auroral protons of that energy, which, as far as anyone else knows, doesn't happen. And then in January 20th, 2005, we had the good fortune to have several balloons aloft simultaneously during what was the second largest ground level solar proton event of the spaceflight era. One of those things that keeps spaceflight managers up at night, because it would have been unhealthy to Lee and his colleagues, to put it mildly. So let's start by talking about the global circuit, because that's an area of my research that's, I think, unfamiliar to a lot of people. Although the researchers who used to work on it include some very prestigious people. One of the very first scientific publications on the subject, or the scientific publication on the subject of the global circuit, began in the middle 18th century. The first publication was in France. But one of the follow-ups to that thread, if you will, was Franklin's famous kite experiment. That would be Benjamin Franklin. So this is an old subject. It's been, people like Maxwell and Kelvin have published in this subject. It's surprisingly how sparse the database is on which our understanding of it is based. But we have, down here in the troposphere, we have thunderstorms. This is at least familiar to everyone here in Houston. Giving this talk in Arizona is a little difficult, but in Houston we don't have to explain thunderstorms. And the thunderstorms are basically charged clouds. And the mechanisms that are as yet obscure, but involve friction of air masses moving past each other, and the electrical properties of partially melted water, which are rather complicated. You get positive charge at the top of the clouds and negative charge at the bottom of the clouds. And that drives a current to the ionosphere, roughly to the level where the conductivity of the atmosphere is equal to the conductivity of the ground. And that starts to occur at about 70 kilometers. At which point the current distributes itself horizontally. About half of it stays in the originating hemisphere, about half of it flows through the magnetosphere, the extreme outer regions of the Earth's atmosphere, extending out to a distance of about 10 Earth radii, and the current flows along the magnetic field of the Earth to the opposite hemisphere. And any given thunderstorm cell produces a current of 1 to 2 amperes. There are roughly 1,000 thunderstorms happening on the Earth at any given time, most of them around here. We actually are one of the hot spots of the world. That current flows back to the ground in fair weather regions throughout the entire globe. producing a current which on a global average is about 2 picoamperes per square meter. Over Antarctica it gets up to about 6. There are the topography or orography, to be technically exact, has a tendency to focus the currents. And this is a subject of, in fact, if there was no global circuit, cloud-to-ground lightning would turn off. Because cloud-to-ground lightning occurs because this circuit, which has relatively low resistance here and only about 200 ohms in the rest of the globe, drives charge to the ground. So you get positive image charges building up on the ground that are quite large, and the current, that's what drives cloud-to-ground lightning. If it wasn't for the global circuit, if there was no global circuit, there would be no cloud-to-ground lightning. There are some other generators. The magnetosphere, which is coupled to the solar wind through the cross-polar cap potential, can drive up to a third of the current in the global circuit. And then thermal tides on the day side of the Earth produce what's called the quiet day ionospheric dynamo. Now this model goes back to Kelvin and to CDR Wilson, and it's sort of a global capacitor model, and it rests on a very meager database. The original electric field data, which everyone still regards as canonical for reasons that strike me as more than a little bizarre, is the research voyages of the ship Carnegie. And over about a 20-year period, they accumulated 17,000 fair weather data points in oceanic regions. And that's the database. Now, the comparison to, well, we haven't had a good global count of lightning strokes until the last 5 or 6 years, when appropriate global lightning stroke mappers were finally flown. But the model rested on comparison of the local time variation of the so-called Carnegie curve with the local time variation of the counts of thunderclaps heard in central London. You know, if you tried to publish that paper today, the referees would laugh at you. But this was 1929, and a somewhat more solid follow-up was published by a guy named Bob Holzer at UCLA in 1956. Then the next study that really had any statistical basis was one of mine in 1999. So the statistical weight of the database on which this model is based is rather meager. But we are, and the thing that's really interesting, the reason we really would like to get a better database is that, you know, the rate of thunderstorms depends on global temperature. So what we have here is a single point, relatively easy to measure, proxy for global temperature. And getting the climate change people to fund our work has been like pulling teeth. In fact, it's actually harder than pulling teeth. And maybe if I have time toward the end of the lecture, I'll tell that story. All right. So I have flown a bunch of balloons in Antarctica in my career. Balloons are the lowest altitude form of spacecraft flown by NASA. NASA actually considers high altitude balloons to be spacecraft. They call it the low cost access to space system. And the headquarters of NASA's ballooning activities, in fact, just up the road in Palestine, Texas, at the Columbia Scientific Balloon Facility. And don't you dare call them the Palestine Launch Organization. They don't like that. Anyway, we flew, I'm going to talk to you about the results from two separate balloon campaigns in 2003 and 2005, both of which were flown from Antarctica. And this is the picture of the 2003 balloons, which were flown in conjunction with my colleagues at ESOS in Japan. We have, you know, the balloon had an antenna wrapped around it. The balloon is, well, this was a 2 million cubic foot balloon, 50,000 cubic meters. Diameter was 50 meters. And we have a payload which is about 340 kilograms of payload, 160 kilograms of ballast. And it measured electric fields, X-rays. It had a precision scientific magnetometer. It also used GPS to measure position and to measure total electron content by measuring the Faraday, I think they're measuring the Faraday rotation of the signals at various frequencies and comparing them. And also we're measuring the conductivity of the atmosphere around the balloon. And this antenna around the balloon gas bag itself measures electromagnetic waves up to 10 hertz, from a few millihertz up to 10 hertz. So, and to make the measurements by the payload clean with respect to possible electrostatic charging in the gas bag, we had about a 100-meter reel-down mechanism. Now, we tried to fly 3 of these. One of them failed within an hour of launch and was cut down immediately and recovered, and is now sitting in a lab in ESOS. I've seen it, and we're still trying to decide what to do with it. The Japanese bureaucracy grinds very slowly. Anybody gets frustrated with NASA bureaucracy, just think about ESOS. They've been trying to decide what to do with this extra payload for 5 years, and we haven't reached a conclusion yet. And they've already paid for it. You know, what's the issue? And the U.S. has offered to pick up the launch expenses, and it's like, come on, guys. Anyway, I've even offered to write the proposal. So anyway, we had two out of the 3 actually got going, and now they were launched. I don't have this figure up here because it doesn't really show much, but the intent was to, in the Antarctic summer, there's still what's called the Polar Vortex, which is a ring of winds going around Antarctica. It's actually relatively well formed in midsummer, and it goes from east to west. So if you launch from the Japanese base, which is in south of the Indian Ocean, at Showa Station, after about a week, actually this is nearly 2 weeks, you're over west of the Antarctic Peninsula in a position basically south of Canada, south of the central U.S. actually. So during the event I'm going to talk about, the balloons were located here. I don't know if you can read this. That's 76 geographic. This is 67 magnetic. And David, I'm going to have to adjust the lights.
Oh.
Actually, maybe.
I think that's, yeah, either way it's better.
Yeah, these guys are over on this side, so. This balloon is about 61 magnetic, and this balloon is around 65 magnetic. The magnetic lines are the red lines going like that. The black lines are showing geographic, and this is at about 120 degrees west longitude. And just for reference, this is the visual picture from Tyros, and this is the infrared picture from Tyros. So we were just on the eastern edge of a large, what is the term? Extratropical cyclone is the correct meteorological term for this kind of storm. Big storm. And, you know, even in summer, you have a ring of big storms around Antarctica. Now, if we want to, since we're talking about magnetospheric physics and the connection of signal phenomena in the atmosphere to the magnetosphere of the Earth, one of the factors that's critical is the magnetic connection to the opposite hemisphere. You know, the Earth is a big bar magnet. That's why compasses work. And the magnetic field lines of the Earth come out of the Earth in the southern hemisphere and go into the Earth in the northern hemisphere. And if you follow the field line from one balloon to the other hemisphere, you find that our southernmost balloon, or our equatormost balloon, equatormost balloon, is conjugate to this region here. This is some data taken in 1650. This would be a map of Canada. And we have the polewardmost balloon is conjugate to here. Now, the nice thing about Canada is that is A, solid land, B, inhabited, and C, inhabited by a scientifically active country which has equipped its landmass with a lot of scientific instrumentation that's quite useful. These points here, actually here, 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 and actually I think it's actually over in here, but then there's another one there, and where is it? It's over here somewhere, are all magnetometers. They're all stations where there are DC magnetometers and in some cases AC or induction coil magnetometers and photometers and all-sky cameras and other things operated by my colleagues at the Universities of Alberta and Edmonton. And it used to be called Canopus, it's now called Charisma, but at this point it was still called Canopus. This location is actually a sort of guest investigator station. It was operated by Japanese colleagues, and this is just an induction coil magnetometer. And I'm going to actually show data from here, 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 and here at various points in this talk. The difficulty is that the time period of interest was around 1600 UT. Well, the time shift between Central Canada and Universal Time is about 6 hours. So this was midday. And even in January in midday, Canada at this latitude is daylit. So the photometers and all-sky cameras were not useful. Okay, now here's a place where I may be getting technical, and if I have to explain things more thoroughly, stop me. These are data from two different spacecraft during the period of interest. The left-hand panel is from a spacecraft in geosynchronous orbit, pretty much over in North America. These are U.S. spacecraft, GOES 8. And this is from a spacecraft called ACE, that stands for Advanced Composition Explorer, and it sits at the L1 libration point between the Sun and the Earth and monitors the solar wind. So it's about an hour upstream of the Earth. Let's see if I can tell you what these various graphs are. This is the X, Y, and Z components of the magnetic field in what are called geocentric solar ecliptic coordinates. What's that mean? Well, X points toward the Sun, so that would be this component. Z points toward the north celestial pole. That's perpendicular to the plane, that points to the north ecliptic pole, perpendicular to the plane of the ecliptic toward the north. And Y is perpendicular to both of them. The Z component is the one which determines how much energy gets put into the Earth's magnetosphere. So when you have a change in Z from positive to negative, you expect the Earth's magnetosphere to start getting much more active. The other orientation here, the change in the sign of X, corresponds to the change in the solar magnetic sector. So in this region here, up until this point, from there to there, the solar wind is mostly, X is mostly positive, which means that the magnetic field is pointing toward the Sun. So this would be a toward sector. But this is what's called a sector crossing, where the magnetic field is now, it's going to be that way for several days, is now away from the Sun. So this is a major orientation change in the solar wind. It's accompanied by a major drop in total field strength. This is total field strength. I think that's total field strength. Yes, it is. So there's a major drop in total field strength. And there's also an orientation change. This is the cone angle of the magnetic field about the direction toward the Sun. And we can see there's this orientation change. Now these other panels here, this is the solar wind velocity, and it's pretty steady. This is actually 440 to 580. Well, that's no change, basically. That's kilometers per second. This is the density of the solar wind. And And we can see here where the amplitude of the field falls off. The solar wind maintains pressure balance. When the field drops off, the density goes up to maintain pressure balance. In magnetohydrodynamics, gas pressure, regular old P, is balanced by B squared pressure. So you either have a region of big B and low gas density, or if you have a region of high gas density, the magnetic field is going to be small. And that's what we have here. We have a jump in particle density and a fall off in field. This is the dynamic pressure that the solar wind is exerting on the magnetosphere in nanopascal, and it goes from around 1 up to several. So we're going to see a major compression of the magnetosphere at this point in time. This is all happening at around 15 to 1600 universal time. And then this plot here actually shows the delay time, calculated delay time based on a model from the ACE spacecraft to the center of the Earth. And it's running around 45 minutes, for those of you who can't read. Okay, so what we see here is that at this time, here at the Earth, now, these are the three components of the Earth's magnetic field measured at the Earth. This is the poleward, normal, and east-west component measured in geosynchronous orbit, and this is the total field. So when this pressure increase hits, you see this massive compression of the Earth's magnetic field at geosynchronous orbit. And that's accompanied by a the fact that the poleward components increased really means that the field has gone from elongated to very dipolar, or even more squashed than dipolar. We also see that starting at about this time, there's all this wave activity. All these bumps and wiggles represent hydromagnetic wave activity taking place in the magnetosphere. This is sort of too busy to talk to, but these are ground-based magnetic signals seen in Canada. Several of the stations I showed you earlier are shown here. This is basically the entire line of observatories, and these are the X, which is basically north-south, Y, east-west, and Z, vertical components. We see the onset of wave activity, but not much DC change. That's interesting, because we would normally expect to see DC changes associated with this kind of activity. Now, in the southern hemisphere, there was a wave event that occurred at this time. You can see that it starts actually before the major disturbance in the solar wind. These graphs, well, let me introduce it here. This is actually from 0 to 5 hertz. Okay, very low, ultra low frequency waves. This is time from 1500 to 1800, and the color bar gives you the power at those frequencies. So we can see that there are, and this is the actual waveform. This was recorded on the more equatorward of the two balloons. And we can see that there is this activity around 1 hertz and 2 hertz, and then these broadband bursts of noise that we can see here in the waveform data. Now these signals are somewhat different. These are 24-hour plots these are from various stations in Antarctica. This is the South Pole. This is McMurdo Station. This is a station P5, which is near the magnetic polar cap. And this station is P2, which is at a lower magnetic latitude than South Pole, basically toward England from South Pole. And what we see here is this signal. This is from 0 to 1 hertz. They're all the same. The frequency is linear, and otherwise the power is basically the same scale as it is over here. Black is no signal. Bright red, which they don't show any of, is very strong signal. But this feature here, this region between roughly 100 millihertz and 1 hertz they're called Pc1 waves. That's a nomenclature which was invented in 1962 in a bar in Berkeley. I'm not actually kidding. By a Russian sitting in a bar in Berkeley. But anyway, and PC stands for, I think it's pulsations continuous in French, but anyway. And Pc1 are the highest frequency. And these discrete events are classic Pc1s. And they're seen actually over most of the southern hemisphere. And to some extent they're seen in the northern hemisphere. I will speak to this graph in a minute. This is a graph of conductivity measured in the stratosphere, measured at one of my balloons. And just notice that there's this enhancement of about a factor of 2 in the conductivity during the time interval when all these waves are occurring. And this is a whole day. So this is 6 to 8 hours. It's a long time period. Question?
Coming back to the left-hand side graph, does it indicate that the wave was trapped otherwise and only at one point, so that particular instant of time, not instant of time, like in that time period, it was coming out? So the trapping of the wave for solar flare, was it due to the magnetic field, and when the magnetic field was...
Okay. First off, there was no solar flare at this time. The solar flare is the next event. But second off, these particular waves are Alfvén waves. They're in the Alfvén mode, which means that both the group velocity and the phase velocity are parallel to B. So they are, in principle, oscillating along a single field line. Now, what people think happens, well, this mode, and this is work I have yet to do and need to do, is thought to be locally unstable in the magnetosphere. It's driven by temperature anisotropy among hot protons. So why these temporal bursts are occurring in this stuff is occurring at the same time as this stuff, but essentially these regions here and this region are very far apart magnetically. They're hundreds of kilometers apart. So this is actually a very different character of event. You can barely see the kind of things that we're seeing here in this event. This is at 1830. 1830 is right there. So we don't really see a big, see that would be, there's 1830 is right there. You don't really see that enhancement except maybe here. So this is, what we're seeing at balloon 10 is not quite the same thing as what we're seeing at the other stations. Now what people think happens is that if you have the Earth and a magnetic field line, there's a region of instability out here, and the waves propagate. They're not so much trapped as guided. We use the term guided for waves rather than trapped. And they come down and penetrate the ionosphere and then spread out under the ionosphere to detection stations. At this frequency, even though they're evanescent in the waveguide, they should be able to propagate several thousand kilometers. Okay, so we have a conductivity increase at one balloon that appears to correlate with a large-scale ULF wave event. This event was global. It was seen, let's see, I haven't got both hemispheres here. This is more detail on South Pole. This is all three components, Z, Y, and X at South Pole. This is data from the Polar spacecraft. And this is the foot of the field line track of the Polar spacecraft. And the foot of the field line track of the Polar spacecraft during the period of interest is basically right over. You see, this is 1800. It's right over South Pole. And the polar spacecraft is actually on the dayside, in the dayside magnetosphere at about 9 Earth radii, near the equatorial plane. So, and these emission features are at the same frequency as what we're seeing at South Pole, and they line up in time 1 for 1. That's virtually never seen. That's mostly an observational difficulty. You really have to be literally on the same field line as your ground station to see that. So this is a very, I won't say that, that's a bad way to put it. It's a unique event. It's, I think, quite important to understanding the wave physics. My problem is I don't have a graduate student to work on it. I have to work on it by myself. And the event is also seen basically all over this region of Antarctica. These stations, P2, A80, A81, A84, are all in this area. Now the balloons are over here. We'll see that in more detail in a second. I may not get to my second event. Oh well, that's okay. So here are my 2 balloons again, near this storm. One of the things they measured was the conductivity. This is the conductivity. The scale goes from 0, it's linear, it goes from 0 to 2 times 10 to the minus 11 Siemens per meter. To give you some idea, copper is around 10 to the minus 4. Seawater is about 10 to the minus 5. Actually, I think copper is better than that, but seawater is 10 to the minus 5. So this is actually pretty low conductivity. The room we're in is 10 to the minus 14. I guess copper's got to be better than 10 to the minus 4. I'm misremembering. Because copper should be more like 10 to the plus 4. Anyway, this curve shows data points measured by taking a probe to a potential, letting it relax, and measuring the time constant. And the time constant is inversely proportional to the conductivity. Formal error bars in the fit are plotted so the data point is the dot, and the solid lines connect the ends of the error bars. So when you see something like this, where the dot is here, the error bars go from there to there, ignore that point. That's bad data. But here, where the error bars just track each other very closely, the perturbation goes along for many hours. You can believe that. That has real statistical significance. Now that's this balloon. This balloon over here sees nothing. Well, it doesn't see nothing, it sees conductivity, but the conductivity is constant. Now, the question is, what caused this? There are 2 hypotheses. One is, it's this storm. The problem with that hypothesis is, there's no physical mechanism to go with it, and as we'll see in a minute, the electrical connection to the storm was actually stronger at this balloon. That doesn't work. The other hypothesis is that the wave event that was going on was precipitating energetic charged particles from the magnetosphere that were causing increased conductivity. Difficulty. We had an X-ray detector on the balloon. The X-ray detector saw nothing. Nada. Zip. Well, okay, that means there were no electrons causing this. Well, at 32 kilometers altitude, if you want it to be protons, to get to 32 kilometers altitude, your proton has to hit the atmosphere with 60 MeV. So the other thing we had on the payload was a vertical electric field detector. And the vertical electric field detectors on both payloads, the solid curve here is the payload that detected the conductivity enhancement. The dashed curve is the other one. Storms, as I mentioned right at the start, tend to drive currents up into the ionosphere. Now, that's thunderstorms like we have around here. Well, in case you haven't noticed, we're a tropical climate. Antarctica's not. Antarctica is not a tropical climate. But these extratropical cyclones turn out to be electrified. This is something nobody knew before this observation. And we still haven't really understood what that means for global circuit studies. But the region near the balloon that saw no conductivity perturbation is much more electrified than the one that didn't. Problem. The strange rheometer data is pretty technical, so I'll skip that. So the question is, what caused the factor of 2 conductivity increase observed by by one of my balloons? I'm ruling out electrons and X-rays. So the ideas are protons or the nearby tropospheric storm. My argument is it's protons. First off, there was a spacecraft up which just died about a year ago called Image. An Image basically, well, you could imagine, has a bunch of cameras, including one that takes pictures in Doppler shifted Lyman alpha corresponding to proton aurora. And unfortunately, the Image apogee was in the equatorial plane during this event, which it precesses, and it was intended to be, when it was launched, it was high above the northern hemisphere. Later on, it was over the southern hemisphere, but in between, it has to be at the equatorial plane. So we just had bad luck. And this is the proton auroral camera. I don't know if you can see the continental outlines. There's Australia. There's New Zealand. And if you think about where my balloons were, they were just over the limb of the Earth. What about there? Well, we can see this proton aurora is present for quite some time. These are all the relevant pictures. During the event where we're seeing what we think has to be the result of energetic proton precipitation. Aha! The hunt's afoot. The other thing is that I showed you that reorientation of the interplanetary magnetic field and pressure increase, or what's called an SI in the jargon of the trade, that occurred at about the start of the event. Both of those phenomena are known to produce post-noon, low-latitude proton aurora. Well, that's exactly where we are. Post-magnetic noon at relatively low latitude. Bingo. Proton aurora. So, there is proton aurora going on. The question is it energetic enough? Well, I went to 2 spacecraft to try and see. This is a spacecraft called Akibono. It's a Japanese spacecraft. It's been up for more than a decade. And then our pop culture quiz for the day. Anybody know where you've seen the word Akibono? Okay. I can see none of you read the URLs that come up on your screen. When Yahoo first started, it was started by 2 graduate students at Stanford. And they did it by basically stealing the university blind. They ran on a Stanford machine. It was actually a VAX. And the machine was actually purchased by a friend of mine to analyze the Akibono very low frequency wave data. It was known as akibono.stanford.edu. And somehow the Yahoo guys got hold of it and co-opted it. I think while Yahoo was running it, it was still being used for the wave analysis, which caused problems for both groups. Anyway, the Akibono spacecraft is still in orbit, still producing data, and it has a detector that goes up to 60 MeV, and I plotted that data here. Each of these color bars is actually a 3-point energetic spectrum, increasing in energy from left to right. Now, the scale is kind of funny. The x-axis is familiar. This is 24 hours in universal time. The Akibono is in a relatively speaking polar orbit, so it tends to scan from south to north or north to south. This coordinate system here is what's called the Mcilwain L Parameter. The best way to think of the Mcilwain L Parameter is it's the equatorial radius at which the magnetic field, or the radius at which the magnetic field line that you're observing crosses the equator. So 1 is near the Earth's equator, and the auroral zone, geosynchronous orbit is 6.6. The auroral zone basically goes from 6 to about 10, and the subaurora region where my balloons were observing was in the 4 to 5 region. Well, guess what I see here? I see protons, and they're enhancing in the afternoon. Now, this is the greater than 16 MeV proton channel from U.S. spacecraft. Actually, it's from 4 U.S. spacecraft. In weather parlance, they're known as TIROS. If you're doing particle observation, they're called the POES MEP Omni detector on NOAA. Actually, I didn't use 13 because it was hard, or 14 rather. It was hard to. It was required a different program. I actually have 4, but I only use 3. And you can see here in the afternoon, now there's some electron contamination in here, but we see this increase in count rate extends up to the auroral zone, goes down, and occurs just when the wave activity is occurring and when I'm seeing my conductivity enhancement. Now, what's the relationship to the wave activity? Well, think back to sophomore physics. A charged particle gyrates around a magnetic field with a frequency that's basically the charge on the particle times the magnetic field divided by the mass. In the equatorial plane of the Earth, the gyro frequency of protons is about 1 hertz. So, at least at these radii. So, these waves are near the gyro frequency of the particles in the equator. So what they can do and do when that occurs is that they're very strongly active in scattering the waves in pitch angle. What's pitch angle? I mean, scattering the particles in pitch angle. Pitch angle is the angle between the particle's velocity vector and the magnetic field. Now, normally, particles are trapped, which means that the region of pitch angle space that corresponds to hitting the atmosphere is empty. We call that the loss cone. But if there's active pitch angle scattering, then particles that are normally trapped get scattered into the loss cone, precipitate, and do the things we're seeing happening. So the presence of the waves appears to be necessary for the scattering of these protons into... all right. I did something no one's ever done before, I don't know why. This is a new format for plotting NOAA pose data. I used a geographical ground track. What a concept. My balloons, there's the 2 tracks. This is just a blow-up of a curve you've seen before. There are the 2 tracks over here. South Pole is here. McMurdo is about there. P5, which had no wave activity, is about there. P2 is about here. And the other stations that had wave activity are over here. And some of these stars are conjugate points to stations where I showed wave activity in the northern hemisphere. Here we can see the protons. Now, the owner of this experiment, Janet Green, was on medical leave for about 1.5 years. It wasn't her issue, it was her daughter's. And so she hasn't really been able to interact with me on this as much. I showed her this stuff in December. She was just back to work. And she went, I don't understand. Protons don't do that. Well, electrons don't either. The region of minimum in the field is here. This is the South Atlantic anomaly region over here. And electrons drift this way, which means that if this was electrons, you'd see a great big enhancement over here, all this green stuff, and nothing over here. Protons drift this way. And when they hit the anomaly, they precipitate. So this is the geographical proton pattern we expect for proton precipitation. And then there are little bitty blobs here and here and in here and here and here, drifting westward, which is what protons do. And the blobs are all at a high enough latitude to be seen by this balloon, but not by that one. Totally consistent picture with protons. Now, I should say, the problem with this is that if these were solar protons, they'd fill in the whole polar cap. And there's a sense that if they were auroral protons, they actually ought to be filling that in too. One of the sort of facts of life in magnetosphere is that if it's energetic protons, you don't get the slot region. So people are very puzzled by this pattern because it isn't really characteristic of protons either. So and this is the greater than 16 MeV channel. There's not enough statisticalness in the greater than 60 MeV channel to actually show you anything. I'm going to stick with my view that these really have to be energetic protons, just because there's nothing else that can produce a conductivity change at 60 kilometers, at 32 kilometers, that corresponds to known physical mechanisms, that doesn't also produce count rates in an X-ray detector. So that's my conclusion. And I guess going slowly and carefully explaining everything, I actually gave this entire talk, including the next half that I haven't gotten to, in 30 minutes in Italy last summer, but I was talking to professionals that I could just sort of blast through some of the detailed explanations of, like that figure with all the panels from the solar wind. I just said, this is solar wind data, you know what it means. As usual, I'm hopelessly over-prepared, so I will stop at this point since my hour is up. Yes?
On that second balloon, since you said it was right there around the greater part of the winter storm, was there any possible, maybe that there was some shielding or something going on from the storm to that balloon?
The balloon is certainly seeing the electric field of the storm very strongly. And there have been postulated mechanisms that, it's been postulated that storms can change the conductivity in the stratosphere. And there certainly has been data, unfortunately of both sides, published over the decades that suggests that can and does happen. But no one's ever suggested a mechanism. And in the absence of a mechanism, I can't answer your question. And that's really why, one of the reasons why, one of my colleagues who's a co-author of this paper would, if he'd written it, would have come up with the other explanation, because he really believes that the storms do affect the conductivity. But he had to admit I had a good point, that with the electric field being stronger at the payload which doesn't show a perturbation, was kind of arguing against it. Yeah, the fact that the field is there strongly means it really isn't shielded. Any other questions?
Questions?
Yes?
I'll just go ahead and throw it out. I think it's totally ignorant. That just got me to thinking, is there any third correlation between storm activity and daily geomagnetic index activity?
Controversial subject. You're talking about tropospheric storm activity. Yeah, there's a whole body of literature on that going back to a guy named Wilcox in the 60s. And the correlations come and go. And it was recently established that the reason is that the correlations have to be cross-coupled with things like the sulfur dioxide, the sulfuric acid content of the stratosphere. And it's just like the other thing that had to be folded in. If you really wanted to see a good correlation between sunspot number and storm patterns, you had to fold in what's called the quasi-biennial oscillation in stratospheric wind direction. And so there are switches, and if you don't in the atmosphere that turn these effects on and off. And we're beginning to identify those switches, but we don't understand the physics. But the more switches we discover, the more we're getting clues. And the sort of leading candidate, if you will, is coupling to the vertical current that I talked about. Because the vertical current can control the rate of cloud nucleus formation through a process called electrocharging of water droplets, and or electroscavenging of water droplets. The rate at which nuclei that can start forming cloud droplets can form in the stratosphere changes depending on how much current density there is. And that's a very controversial subject. It's a very controversial body of work, and it's work very much in progress. Whether or not you even believe the statistics depends on who you ask. There are statisticians who, well, they don't like the selection process associated with whether or not there's with the quasi-biennial oscillations. They think that's unfair, and they don't like the selection process based on sulfuric acid content in the stratosphere. They think that's unfair. But really, in terms of what we are beginning to understand about the physics, I think you have to put those switches in. When you do, the statistics leap out at you. So yes, there is connection between, we've known for a long time that there's a connection, for instance, between sunspot number and the direction of the sort of really weird little climate things that really have strongly connected sunspot number, like the wind direction in Athens, like that. But perhaps more economically important, drought cycles in the western United States. Those tend to have a 22-year cycle. And they also have a longer cycle, which is proving very unfortunate right now. If you're planning on moving to Los Angeles in the next few years, don't. Lake Mead is predicted to run dry in 2013. And this is partly for this reason, some of this coupling. It's how the sun couples to climate on any time scale at all other than the diurnal, which is and the seasonal, both of which are obvious and well understood, is not known. The sun is a variable star. That's pretty well established, but it's not a variable enough star. So there have to be amplification factors in the system, and it's the amplifiers we don't understand.
How big was the change in conductivity?
Factor 2. Yeah.
My name's Alex Monchak. I'm in the engineering management program here at the university to try to get back to work with NASA. I had a question from the title, the effects of solar energetic particles and radiation on the Earth. Can you extrapolate that to President Bush's return to the moon and Mars mission as energetic particles and radiation being the primary risk to his vision of going back to the moon and going to the Mars? And my second question was about the graduate students. You mentioned that you needed help from a graduate student. Mm-hmm. Is there mechanisms in place to have graduate students at UH Clear Lake working with professors at the main campus?
Oh, I love that question. All right. To answer the first question first, because it's actually easier, the particles we're talking about here are confined to the inner magnetosphere. So once you're outside of 10 Earth radii, and the moon is at 60, you're okay. And so that's why, for instance, a number of the electric propulsion scenarios for transiting to Mars have the vehicle do its first 30 days unmanned, and then we have to have a chemically boosted intercept with, say, the CSV carrying the crew, because you want to get the vehicle through the radiation belts before you put the crew in it. But the radiation belts are relatively confined, and the real issue is not the radiation belts. The real issue is what I'm about to show you. I'm going the wrong way. Come on. The real issue is those guys. That's a Class X7 flare. It produced the largest ground level GeV proton event in 50 years. But they happen once every 50 years. We had 7 minutes warning. 7 minutes between when they saw the X-rays and the protons hit.
One every 50 years that you see on Earth.
This event is sufficiently global in the heliosphere that, also that doesn't matter. If it's once every 50 years you see on Earth, it's once every 50 years at any given one location in the solar system. Being somewhere else.
Some anisotropy.
No.
You don't think so?
No. Because they're randomly distributed and evenly distributed in longitude. Any anisotropies are going to be north-south, and those don't matter. So this fills the entire heliosphere with GeV protons. And this is a much more dangerous event than the kind of auroral stuff I'm talking about. Because, for openers, you get 7 minutes warning. Now, if you have an appropriate cocoon, 7 minutes is plenty of time if you're inside the spacecraft. If you're on a EVA, that's a big problem. You better hope your spacecraft has a big magnet, because that's what you're going to need. Because that's about the only thing you can get inside of fast enough.
Do most spacecraft protect against that? Will most spacecraft protect against one of those, or would they have to build?
You would need a storm shelter, probably a fairly thick polyethylene cylinder.
Like a safe room or something?
Yep.
Because even the International Space Station's a lot lower.
Yeah, the International Space Station. See, the Earth's magnetic field is a fairly good shield against this stuff, except because even this event, strongest ground level event in 50 years, most of the stuff was cut off because by the Earth's magnetic field at a latitude of 50 degrees. Equator to 50 degrees, you were pretty shielded by the magnetic field. It's just that. So. Actually, the real key of this slide is that the ion count rate was so high, the X-ray count rate was so high, it basically killed my detector because it drained the high voltage supply with so many counts were coming in.
We're talking light speed.
Huh?
We're talking light speed protons.
No, the protons got here at C/2.
Yeah.
They were 7 minutes after the photons.
Yeah, because it's about 8 minutes to the optical.
It's damn fast.
Yeah.
This is not 20 hours or something.
No. 20 hours you get the geomagnetic storm.
So, yeah, what energy are we talking about?
GeV. Yeah, so that's... Now, to answer your second question, okay, now I can only speak to physics. I can't speak to management, although I have a meeting tomorrow about the whole issue of management degree development. I'm not in the College of Business, and that's kind of above my pay grade, but I'm having the meeting anyway, because the vice president has told me, go, we'll settle the details later. But in physics, what we have is what we now call our joint UH-UHCL Physics PhD program, whereby the core classes will be offered either directly here by David and his faculty, or through by central campus faculty who either live in this area, are really committed to the profit margin of Exxon. I live in Memorial, or are teleconnecting. And so we are really trying to set up the courses so that the courses can be taken in a reasonable way by people who have full-time jobs at JSC. The research is more problematic. The research, you have to hook up with somebody who either has a joint appointment or a full-time appointment at main campus. And then you have two choices. You can work with a professor who has a project that is either, data analysis that can be done over the, data analysis works best. But what I've discovered the hard way, by having students sort of run into the buzzsaw and bounce, is if you actually want a PhD and want to do the research, a PhD national average is 19,000 hours of work. We at the university have it doesn't matter if you're part-time or not, this is a hard limit, 10-year limit on the PhD enrollment process. Do the math. That means that your part-time effort is at about 40 hours a week. It isn't going to work unless you can find a topic at your job that's your PhD thesis. Now, some of us are try hard to be accommodating on that. I don't know how many of you know Charlie Armstrong. Used to be an EVA dude. I don't know what he does now, but he did a thesis with me on the physics of EVA safety equipment back in the 80s. And I was perfectly prepared. And actually what we ended up doing, since it was sort of abstract, his thesis constituted a proposal to build some of the equipment. The thesis was that was ultimately funded at a small level, and I got the equipment about half. It was about half built on 9/11. And it was being built by a green card holder from Brownsville, Texas, who made the mistake of being a Canadian citizen. On 9/12s, I was told she can no longer work on that project. So I haven't. That project is sitting on my lab bench unfinished. But the students who've been most successful in getting PhDs by this mechanism are all guys who work in the space radiation group, SRAG. SRAG has generated a lot of PhDs because they can do their PhD at work. The only other project, we have had some PhDs that are in various stages of progress at what used to be the ASPL, now Ad Astra Rocket Company. And that works fine if the guy can be employed there full time. It doesn't work at all if you're trying to do it nights and evenings. So some of us are more accommodating than others. I mean, I'm perfectly willing to kind of supervise something I know only little about, learn as I go, that's already your job. And we can find degree problems that fit into what you're already doing. I'm also an engineering professor, so as long as it's either power systems or telemetry, I can even do that in a spacecraft development side of the house. I wouldn't want to do it outside of those two fields, because I'm just not competent. But we are to really let you open. At the request of our new president, I wrote a memo to the vice president for research and to the chancellor on what faculty we need to add and what process we should institute. And I was thinking in terms of science and engineering faculty, and my number was like 30. So that we can support the market that we see coming in terms of guys like yourself and a whole lot of other people who will be hired or have already been hired to support the Constellation program. Not to mention the fact that there are still offices 2 blocks over that way where I'm the young fellow. You guys know those offices. I'm 62. Now, sooner or later, nature will take its course. The youngest of the Punamunda guys is now 89, and so that group is getting thin on the ground. So we expect new employees soon, and those guys a lot of them are going to want degrees, advanced degrees. So we're certainly thinking in those terms. Now, in terms of management, I got a memo last week that it's not just U of H that's thinking this way. There are people in upper management at JSC who are thinking this way, except they're actually thinking about degrees in space flight management. That's my meeting tomorrow. And I'm kind of going, well, I'm not in the College of Business, and this is way above my pay grade, but I'll have the meeting.
Because the nice thing about the engineering management program here, it's in the same school as Dr. Garrison. It's not in the business school, and it's developed for engineers with engineering background, and it's not management oriented. It's for the engineers to go up that management chain. And so that's the same thing that space flight concept would be, I would think, would be in the science and physics.
You haven't read the document. They're looking at something that comes out of the law, the College of Business and the College of Management. I have to steer them differently because that, frankly, that goes with the attitude that if you know how to manage, it doesn't matter if you don't know how to build it. Now, from the university perspective, where every university president was a scholar first, that's kind of crazy. I have to figure out a way, how do I say that politely tomorrow?
Thank you.
Good luck.
All right.
One more question?
Yeah, just another quick correlation question. Any known correlation between the electric current, global electric current, and noctilucent clouds? There is an electrical interaction with noctilucent clouds that's studied by my friend Bob Holtzworth from the University of Washington. But
I don't know that anyone has shown a correlation between the occurrence of noctilucent clouds and activity level variations in the global circuit. All right.
All right, so let's thank our speaker.